So I'm Ali Benamara, your instructor for today, and welcome. And please first verify that you are able to log into Databricks, those temporary accounts that they were handed out to you. And two, if you can connect to the file under tinyurl/sseds01, and that's the one we're going to be using all day long. And that's the student's reference file that has all the information that we will need. There will also be a Spark meetup today between 6 and 9 p.m. in room 312, just for your information. Okay, so let's get started. So even though today it's a data science course, I'll try to cover as much as I can when it comes to core Spark, but it's we're not going to spend a lot of time on it. We'll spend most of the time on doing mostly supervised and unsupervised at the end of the day, but I'll try my best to cover core Spark as much as I can. So let's start with this slide here about Databricks, which was founded in 2013. They are behind Apache Spark, and 75% of the code behind Apache Spark was written by Databricks. This is me, a little bit about my background. Sorry, I have to move this a bit, I guess. Sorry. Is it better? Okay. So again, as I said, my name is Ali Benamara. I was a senior big data consultant at AWS in Boston prior to joining Databricks. So I did a lot of work on designing architectures for data lakes and using mostly AWS stuff, Redshift and Kinesis and all that, as well as Spark on EMR. And prior to that, I was at digital signal processing, working for companies like Polycom, ZV, Broadcom. And currently, I'm still doing some research on exabyte scale dimension reduction using a robust PCA, which is an unsupervised. So what are the objectives for today's course? So we will cover mostly Spark ML, especially the new Spark ML, because there are machine ML lib based on RDDs, and I'll talk about that. And there's this new API, which is Spark ML, which is really based on data frames. And once we go over the data frames, we'll see the advantage of using the data frame over RDDs, at least for now. And so we will be looking at how we can do supervised and supervised, and then evaluate models using metrics, as well as how we can assemble pipelines when we do machine learning on Spark. We will see also how we can use cross-validation to do some hyperparameter tunings, and understand the strengths, patterns, mechanism, and limitations of Spark ML. So what's not going to be covered in length today will be things like Spark Core, even though I will try to talk about that because I looked at the pre-class survey, and I see that at least a third of the people here in the room are kind of like new to Spark. As we will not cover the math behind machine learning, because we're going to be, even though I'm going to touch a little bit on some of the topics there, just because they are directly related on how to look at the parameters used in Spark and how to tune those. And we're not going to go a parade of algorithms out there, and then you're more than welcome to look at the documentation for that. Okay, so this is the layout for the schedule for today's class. So basically from 9 to 10:30, I'll try to cover the core and about Spark, as well as we will start looking at supervised linear regression. And then we will take a half-hour break at 10:30, And then we will resume at 11, looking at still supervised, and it's going to be logistic regression and how we can do that on using Spark ML. An hour lunch, and after that we will continue using decision trees and look at how we can use touch on scikit-learn, and at the end of the day we will see how we can do unsupervised machine learning. There will be limited in-class Q&A, but we have a Q&A parking lot file that's, and the link is on that tiny URL, student reference file, where you can go and just add the question in there, and we will make sure to answer it after the class. So you will be using the Databricks community accounts today, and I think you were given those temporary credentials. But you know, the code and the content that's going to be using today in those accounts, they're going to stay there for a month, basically. But then you're more than welcome to move them to your personal free community accounts on Databricks as well. And I can show you how you can export that stuff and then import it later into those newly created accounts. So if you have successfully logged in, this is what you should see. This is the welcome screen on Databricks, and I hope you all can see that. So those free accounts are limited resources, basically. They are 6 GB of RAM containers, and they all run on EC2 machines, by the way. And the driver and the executors are running together on those, inside those containers. And they are using 8 threads, basically simulating Spark in the standalone mode, which is kind of like a fake cluster, not the real one. The data, we will be using small data sets. Obviously, you can't do like large machine learning projects inside those accounts. And then, so when do we use Spark ML? It's basically when, you know, you want to predict data sets that are too large to fit within a single machine. You know, we all know that doing machine learning on one node is great when you're using things like R or scikit-learn. But then when you have a large data set that you want to, you know, play with it and discover patterns in it, then that becomes problematic. And that's when you start looking for platforms like Hadoop and Spark or Mahout or things like that. So in this case, Spark beats those, at least beats Hadoop when it comes to speed when you're doing machine learning. Also, Spark doesn't have all the algorithms that probably you're used to on R. They're still not there yet. So there's work being done kind of like to port all that stuff into Spark, but there still doesn't support all what you can see in R and scikit-learn. MLlib and Spark ML. I'm just going through the slides quickly here, but even though I'm going to focus a little bit more later on those, and what's the difference between MLlib and ML. The main difference here is that Spark MLlib uses RDDs, and Spark ML uses data frame. And then when we start talking about the data frames, you'll see the advantage of using the data frame and what data frames bring to the table in terms of optimization and things like that, that the RDD just can't give you, basically. And now they're doing feature parity between MLlib and ML. And then once they port everything from MLlib to ML, then basically MLlib will be deprecated. So MLlib was in maintenance mode starting last June when Spark 2 was released. And as of Spark 3, it will basically be deprecated, and you will only have access to ML, which is kind of like a layer that sits on top of Spark. I will show you a graphics here, because as we say, a graphic is worth 1,000 words, which explains in details why the data frame is better than the RDD. So I'm just going to skip this one for now. And this is where you can find all the docs if you're interested in learning more about Spark ML programming. They all mostly sit under spark.apache.org. Okay, so I'm going to stop here. Were you all successfully logging into your accounts? Okay. So basically, this is the survey I get back from you guys. And as you can see here, when we look at, let me make this a little bit bigger here. So we have a mix of, the audiences really have different backgrounds when it comes to learning about Spark. You know, it's basically, a third is basically new, a third are experts. And then in machine learning as well, you can see the layout here is basically, you know, from zero in machine learning to experts. So kind of like, I'll try to, you know, this will basically define the pacing for as we go on what I need to cover and what I need to skip here. So let's go back to, if I can move my mouse. Okay. Okay. So if you log into, if you click on your workspace, for some reason I can't manage my mouse here easily. If you click on your workspace, you will see this layout here where it says prepare your work. We're not going to go through that 00 just because you have done it already. I mean, you were provided with login credentials. Let me show you what it looks like, just at least you can understand what it does. If I can control the mouse, sorry. I don't know what's going on here. So basically, we have done one, because you were provided those login accounts. Now, once you logged in, you saw that you have files in there, right? So that will be step 2. So we're skipping step 2. Usually, we have to upload those DBC files. So that has been done for you. Step 3 is mount the data sets. And probably we will not need this, that for this one here. And step 4 is how to install third-party libraries. We will not be needing to do that as well, but I can show you how to do it for you to use later, especially if you do like Spark streaming and you need Kafka to be in there, for instance. Then I'll show you how to upgrade, to load the library to use Kafka along with Spark streaming and things like that. So I'm just going to skip that for now. So let's go to 20. Are the clusters all up and running for you guys? Do you have clusters up and running or no? No? All right, so first thing we need to do is to create a cluster. If you click on that cluster tab. You want me to go to the previous page? Oh. So basically, you go under your name, you should have a list of all those notebooks in there. And then in order to create, well, first let's create the clusters and then we'll navigate back to those notebooks. Are the clusters up and running? You have up and running? Okay, so in that case, then you go to, under your username, you should see a list of these files here, and then we'll just click on number 20. Yes. Yeah, I'm having issues moving the mouse, though. Here we go. All right. Is that better?
Excuse me. Cluster is not running for me.
Cluster is not running?
No, it's not there.
Okay, so let's make sure you have a cluster up and running. And how to do that, you need to go under Cluster, the tab here on the left. And if you click on it, you should see a cluster up and running in there. If it's not, then just create a new one. Okay, so this is notebook number 20, where basically we talk about the data frames, and we talk about the RDDs, and those are the cornerstones even before we can do anything like machine learning or Spark streaming or any of those components that sits on top of core, Spark core. And so in this notebook, we're not going to do it because it's a long one, but at least we're going to go through it and then tell you a little bit about what the data frames are and how they compare to the RDDs and why they are better than the RDDs. So yes. Okay. So if you click on Workspace on the left, yes, and under that folder, then you should see, my layout is different than yours, but you should see all those notebooks under SSE, right? You see it now? Okay, perfect. So what's the idea behind the data frame? So when Spark started, actually it was based out of RDDs, right, which are resilient distributed data sets. So even we don't care about the last D because they're just data sets. What really matters there were the first R, resilient, and the first D, which is distributed. So because we live in a big data environment, as opposed to before, where basically we moved the data to the code when we were just in one CPU environment, now big data changed all that. And now instead of doing that, we're moving the code to the data just because we can't move the data around, right? So this is the big data environment where we have a lot of mini nodes and big data sets that are distributed over those nodes. Now, the R, it's the resilient part because we need to make those systems really robust when we lose data or when we want to recreate that data, or and that's really was brought up by Hadoop, if you remember. I mean, Hadoop 1 especially, where really HDFS was intertwined with MapReduce, right? And that was like when Hadoop started at Yahoo, and then later on, we derived Hadoop 2, and in Hadoop 2, basically what we did was to separate MapReduce from the storage, from HDFS. And then what we ended up with was really HDFS at the bottom, and then a new layer called Yarn, yet another resource negotiator. And then MapReduce became just a block that sits on the top of all those. So we had in Hadoop 2, basically we had MapReduce sitting on Yarn, sitting on HDFS. And now, we didn't like MapReduce because of the way it computed and all that. It's great for batch processing, but when you're doing things like machine learning, when you need to go back and forth to your data, doing a map and write into disk and then read into the reduce was just painful, very painful. And that's where, when Spark came in, it really shined because that transit through the disk was basically replaced with memory instead of disk. Now, when Spark came in, it came in different flavors. So it could be run like in local mode, if you would just do it on your machine, or it can be done in a standalone mode, which is kind of like a fake cluster, where basically you have the driver and the executors, but the executors are just threads, you know. Or it can be also run into Mesos, right, or Yarn. But the one that's really out there used a lot for Spark is really Yarn. And there is a reason behind that is because Enterprise mostly invested a lot of money in Hadoop. So they had already HDFS in there and Yarn in there. So it made just total sense to have Spark running on Yarn, right? So that's why we can have Spark running in different environments, which are Yarn, Mesos, which Mesos used a lot by R&D as well. Standalone, which is the case that you have here, where basically you have the driver and the executor running together, or you can have it running in a local mode. When Spark came in and it was using just the RDD, then we needed to be able to do this resiliency in case when we lose some data, just because we were running on commodity hardware in this new big data world. So a lot of things can go wrong, right? And what happened if you lose some of the data, then you should be able to recover that data. And how do we do it? You do it through a bunch of stuff, including creating a DAG, you know, like a notebook where basically you just record what you do. Using laziness, you know, when you're trying to do stuff, you just don't execute them right away, but you just keep track of what you want to do, and you do it later. And immutability, because once you create an RDD, then you have to, if you want to create a new one through a transformation or a change or something, you have to guarantee immutability in there. And how does the RDD thing works? You have to walk backward, basically. So you issue those transformations which are lazy. They don't execute right away. But all you're doing here is just logging those tasks or steps that you want to do until you hit the action. And the action is the one that triggers the whole execution. And what Spark does at that point is basically it starts walking backward from the action, you know, going like one step back. Like let's say you read from S3 to create a new RDD. Then you have that new RDD. Then you do a transformation on it to create another RDD. Then you do an action at the end, and then that's when things starts executing. And Spark keeps walking backward to see what it does, what it needs to do, based on that log, which is called the DAG, Directed Acyclic Graph as well. That was the RDD way. Then we started thinking, how can we improve that? Because RDDs were just collection of objects. They were distributed, but they were collection of objects. And one way of improving that was adding a schema on top of those collections. So now with the schema, we can use techniques that were really known before on how to basically optimize the code out of those schemas. Because once you add a schema, it becomes a query, right? So all that code now can be optimized through a query. And this is what this picture shows here. The Catalyst Optimizer is the champion component basically in that picture, because that's what it does everything. And then we're going to go over that, and if you understand that, then you will really understand what Spark does under the hood. And I'm going to go into more detail about that. So the first idea was that can we keep the API the same? Meaning like once you create the data frame API, can we keep it the same? And why? Because if you remember, Spark has Spark Core, which is the main layer there, right? And then it has 4 components on top of it. For those who are familiar with Spark, they should probably be familiar with this picture. So we have Spark SQL, we have MLlib, we have GraphX, and then we have Spark Streaming, right? So When the data frame API came along, and then people, they just loved it because it solved a lot of problems, especially through the catalyst that I'm going to go into and describe why. Then we started porting all those components from using RDDs to use data frames instead. So Spark SQL has been updated all along. It's very robust now. MLlib, it's being ported from using RDDs into using data frames, and now it's called ML. GraphX has been ported to use data frames instead of RDDs. Now it's called GraphFrame instead of GraphX. And then Spark Streaming, it uses RDDs. Now it's being ported, especially starting last June 2006 with Spark 2, to use data frames instead of RDDs. And now it's called structured streaming instead, right? Spark Streaming has a lot of pain points in there. The biggest one would be if you are streaming data into Spark, you are not in control of what's going on in the payload, right? So all you can do is just say, I want to define a batch interval, and every batch interval give me an RDD. But then if you have events inside your data, things like timestamp that you want to use, you can't do that in Spark Streaming because it uses RDDs. Structured streaming will allow you to do that. And then you can look at those events inside your streams that are coming from Kinesis or Kafka, and then you can decide on a logic based on that, right? And you can do that, why? Because they are based on data frames, which means they have a schema on top of them. And this also solves another big problem that enterprise faces a lot out there when they are in the big data, is trying to do something like what they call the Lambda architecture. I don't know if you've heard about that, where basically you have something that came in that's batched, and then you're trying to assemble that with what's coming in through real time. Structured streaming will allow you to do that, probably not now in this version, but it's coming, where basically it will keep an unbounded table for you. It just keeps growing the table that comes in, and then you have a regular data frame. The stream data becomes just a regular data frame that you can join with even static data frames out there. So you can do things like join a database from batch with something that's being streamed at the same time. So data frames change the game, basically, when it comes to Spark. And that's the idea now, is basically change all those components to use data frames instead of RDDs. And today we'll spend a lot of time on MLlib and see how things changed there and what we can do. But if you look at graph frames, now they are very powerful components there, because graph frames, they come bundled with a bunch of algorithms that you can use even in machine learning. Things like what's the shortest path or things like that, Structured streaming is very important even if when you do machine learning, because you may end up in a situation where once you create the model, then you need to plug it into an environment where you have a streaming application, right? So data coming in real time. Spark SQL is basically the main component now that's being used for all the other three at the same time. Another big thing that the Catalyst brought to the table is the fact that if you look at this graphic here, you will see that before, when we had the RDDs, if you came in from Python, it was a lot slower than Scala. Why? Because Spark is JVM based. So really you are in a Java environment, right? Even when you're working with Scala. And then what happened is, if you write something in Python that the JVM doesn't know how to resolve, would do, then what it does, it will ship that to a Python process. And then that shipment, you will incur a penalty, of a round-trip penalty because of that. Because your code is in Python, it will need to go to a Python process, run there, and then come back, and then it will be penalized because of that round trip. That's because the RDD, that's how they did it. Now, with the new Catalyst, that's a different story, because with the new Catalyst now, when you enter the Catalyst, you are entering the Catalyst as a query. And you are entering the catalyst as query because of the schema, right? Because of the schema, then it will allow you to do that. So your code will become a query, and then that query will get analyzed exactly like the Oracle way, if you remember, used to be. It will be analyzed, and then the catalyst will try to look at that and see if it can tune that query or even make it better, and then create a bunch of physical plans. And then after that, it picks the best physical plan based on a cost algorithm. So there's a cost algorithm in there. It creates a bunch of physical plans, and then it decides on the best one, and then it turns that physical plan into RDD code. So really what we did here is we didn't get rid of RDDs. We just hid them. You don't have access directly to the RDD as it used to be. So if you want to think about this, you can think about this like assembly language versus compiler. So when people started doing DSP back then, creating something in DSP using machine language, it was painful. We spent a lot of time. And then when compilers came along, they made the life of the developer or the software engineer a lot easier. Because now all you have to do is just write your code in C. But then the compiler will take care of translating that C code into machine code. That's exactly the same thing here. Instead of you writing the code in RDD using .map, .flatmap, .reduce, which can be very involved because you need to know what you're doing, what you do, you write it into a query. Whether you use the data frame API, which really looks like plain SQL, whether you do it in plain vanilla SQL, once you write that code and it hits the catalyst, then the catalyst will look at that query and see how we can change it and do better than you. And it has been proven that usually you cannot beat the catalyst to that. So let me give you an example of what I mean by that, what the catalyst does in there. Let's say you are in a situation where you are joining two data frames, which is kind of like the most difficult and expensive thing that usually you can face, right? When you have like two big data frames that you're trying to join. And if you're not careful, what happened is you will be in a situation when you have a Cartesian join, meaning you have a big off and square situation here, right? And so what do? What the catalyst does, it tries to look at what you're trying to do. So let's pick an example here. Let's say you're joining two data frames, and then after the join, you do a filter operation, right? And then the catalyst will say, okay, so what is that filter operation? Let's assume that filter operation that belongs to the second data frame. Everything that filter does really comes from the data frame number 2. So what the catalyst does in that case, it moves the filter down before data frame 2. Instead of joining directly the data frames, it will filter data frame 2 and then join. Just by doing that, it already reduced the complexity, right? And then it's going to do a lot more. It's going to look at where are you getting the data from? Let's say you're getting the data through JDBC, which is a database, right? If the catalyst sees that, then it's going to say, okay, why am I doing the filtering to start with? Why can't I just ask the database to give me the filtered data at the source? And if that's the case, then the catalyst will issue a push-down predicate, and it's going to ask the database for the data instead of the Spark doing the filtering. So you started with joining two data frames in a filter, and you ended up with a filter operation that got completely eliminated for you, right? And then your data will be already filtered from the database itself. In that's the stuff that you can do by on your own. And that's the stuff that the catalyst is really good at. So basically, it looks at the query, it creates a bunch of flavors of that query, it picks the best one, and then it creates a bunch of versions for physical implementations, and then it picks the best one based on an algorithm, and then at that time, it's going to ask the AST, the abstract syntax tree of Scala, here is the physical plan, please give me the bytecode for it. At that time, the AST will generate the bytecode, which is the RDD code. So this is definitely a lot better than you writing the dot map, the dot reduce, the dot, all that stuff. But you may ask this question, like, I mean, am I not just going to use RDDs at all? The answer is no. Because if the data frame API does not support what you're trying to do, then you will still need to do it at the RDD level. You still have that option. You can still drop down from the data frame to the RDD, and you do that obviously through an API called .rdd. And if you do that, you have a data frame and do .rdd, it's going to give you the RDD version of that. Then what do? You do as usual. You are on your own. You do the stuff that you want to do at the RDD level. But keep in mind that if you are in Python, you will be penalized, for instance, right? Versus if you're in Scala. So you got to understand that stuff. So try to stay away from that unless you have to. And the data frame API now offers a lot of things that can be done without even going down to the RDD level. Does that make sense? Okay. Spark comes bundled with data sources that it supports out of the box. Obviously, it started with Hive, because everyone needed Hive. Everyone loved Hive, even though it's slow, but everyone loved it. So that Spark, when it came out with support for Hive, right? And because of that, prior to 2, we had 2 contexts in there. So we had the SQL context and we had the Hive context. And people, they got confused which one to use, and that was always a confusion, right? And what people did most of the time is that, okay, let's just go for Hive context. Why? Because Hive context is a superset of SQL context. So it does everything that SQL context does, plus it will allow you to talk to Hive Metastore, right? Because now, in big data, people, they created tables, and then they needed to save those tables permanently somewhere. And then that way was Hive Metastores, right? So basically, if you have a table in Spark, you can either keep it temporary there, or you can save it permanently somewhere. And that somewhere is the Hive Metastore, right? So people, they always used Hive context instead of just using SQL context, just to be able to do that. And Spark, when you launch or create Spark in your environment, it creates a default Metastore. But there are ways of how you can hook by just changing a flag in the configuration folder of Spark, of how you can point Spark to your Hive Metastore instead, if you have tables that were created from before in there and then you want to take a look at it, right? And in Spark 2, to remove all that confusion because of this Hive SQL context, now they created one entry point to Spark, and they called it Spark Session, which is really Spark. And that's what we're going to be using today. When we talk to Spark, we will be using just the Spark Session, which is Spark, which under the hood, it still has the SQL context in there if we in case you want to refer to it, you know. But Spark comes bundled with a few data sources, things like Hive. It is supported out of the box. Things like JDBC, it is supported. Let's say you want your Spark to talk to a database, then it's there. Things like Parquet, just Parquet, it's really gaining a lot of momentum out there, you know. And when you see a lot of big companies behind it, and I mean companies, highly regulated companies like NASDAQ and FINRA, for instance, and when they did some benchmark measurements on comparing Parquet versus ORC, which are both column-based file systems, file formats, they found that Parquet is 25% faster than ORC when encryption is involved all the time. So when you are in situations like that, when you have to encrypt your data at rest, in transit, and all the time, Parquet just beats ORC at that game, right? And Parquet has been gaining so much momentum now that it becomes like a second nature when Spark is concerned. So Spark really talks well to Parquet and uses Parquet a lot. Another reason Spark uses Parquet is when you have files that are saved as Parquet on disk and you read them in Spark, Spark gets the schema automatically from Parquet. Doesn't have to do anything. Right? This is really good because if you have a CSV file and you don't provide your schema, what happened is Spark will have to do one pass over your data to figure out what the schema is, and a second pass to get the data. So if you're not careful or lazy, and then you just rely on Spark to infer the schema for you, and you're working with the CSV file, which is most of the time, especially in machine learning, then what happened is Spark will have to do that one pass to get the schema and a second pass to get the data. One way I've seen is that for people to read the data, filter it if needs be, and then save it as Parquet file, and then start doing the machine learning process afterwards. So those are the things that you need to keep in mind. If you want to do something that's not supported out there, out of the box by Spark, things like talking to Redshift, for instance, right? Or talking to any other product which is not out of the box, then you will have to use your connector for that, or connector for that product. So you'll have to go get the connector for Redshift and hook it to Spark to do that. And the place to get all those connectors is spark-packages.org, basically. And then those are free and open source, and you can get them from there. So this is the important component that in Spark now, which is the catalyst, basically. So when you hit the catalyst, you are coming in with a query, right? And then after that, a few steps gets done. Among them, you resolve the unknown through the catalog. You create a bunch of logical plans. Then you pick the best logical plan. You create a bunch of physical plans. Then you pick the best physical plans based on the cost function. And then you call the AST to create the bytecode, right, or the RDD code for that. What's good about this is the fact that it doesn't matter how you came into the catalyst. I mean, you come in through Python, or you come in through Scala, you come in through R. It is the same in terms of performance. This is a big, big winner over the RDD version, right? Because if you, as I mentioned earlier, if you were in the RDD and then you were in Python, you will incur a penalty in there because the JVM doesn't know how to execute the Python code. Then you will have to ship it to Python process and come back. In here, everything will be done through a query. This probably, sometimes I ask these questions like, which one is better? Is it better to just use plain vanilla SQL? Or is it better to use the data frame API, right? And sometimes people, they get confused, but the answer is it's different. It's the same. It doesn't matter whether you use plain vanilla SQL or whether you use the data frame API, as we will see later in the hands-on. We will be using both. We will be using the data frame API. We'll be using the plain vanilla SQL. But in terms of performance, it is exactly the same when it goes through that catalyst component in there. This basically just shows you how less of a code now using the data frame API than Spark MapReduce. This is comparing Hadoop to Spark, and hopefully you can see the difference. It's huge, instead of using it between MapReduce and RDD Spark. And then even after that, this is the map and the reduce by key and all that stuff using the RDD, but definitely using the data frame API is a lot better, a lot simpler. And when you look at the code, you can right away infer what the code is doing, basically. Okay, so I'm gonna stop here about this data frame, because this is like Spark core, and it's not part of today's training. I wanted just to point to you what the data frame is, which is really an RDD with the schema on top of it, right? And the schema just plays a crucial role here, because of the schema now, we have a query that we can optimize through the catalyst. And at the end of the game, the code will be a lot better than us writing that RDD code, basically. The data frame itself has a problem. And the problem that the data frame has is the fact that it wasn't strongly typed at compile time and runtime at the same time, right? So it was strongly typed at compile time, but then if you, let's say, you have a column there, because now we have a schema, and then that column is string, and then you refer to it as double, your code may crash at runtime, right? To solve that problem, then the people behind Spark, what they did, they took stuff that was really good at the RDD level, and they added it to the data frame API. So they added two things to the data frame API, and they created what's called the data sets right now. So what the data set has is everything that the data frame has, plus two things. It is safe at compile time and runtime. It's exactly like the RDD. And it will allow you to do the Lambda functions. Because if you are in the data frame API, you cannot do what I just said earlier if you have your own secret sauce that you want to do at the RDD and it's not provided by the data frame API. You cannot drop to the RDD level and do that in the data frame, right? You will have to be at the data set. The data set will give you that possibility. So if you have the data set, which is the data frame, plus these two things, type safety and Lambda functions, then you can do like what you used to do at the RDD level. Yes?
Earlier you said that the data frame had a .RDD that you easily flip it to an RDD. So is that a data set?
Okay. Let me clarify. Okay, his question was earlier I said that you can drop from the data frame to the RDD. Now I'm just kind of like telling you that you can drop to the RDD when you're in the data frame. That kind of like contradicts the things, right? The way now the data frame is defined in the code, in Spark, is really as type def data set of a row. So you can think about the data frame really as a special data set, which is a data set of a row, right? So you can still theoretically do some RDD stuff, but not a lot, because you are constrained by the row data structure. Now, if you want to be really free to do whatever you want to do at the RDD level, then you have to be at the data set. Does it make sense? Okay. Okay, so we're done with this. Now, if I go back and I go to Scala, by the way, we have the code kind of like duplicated into Scala and Python. So I'm just going to do Scala, and then later on I will run some of the notebooks in Python. But you're welcome to choose any language you want. So there's another one that I wanted to talk about before we start the notebook on machine learning. Is this ML-lib data types. Because ML-lib or even ML uses a few data types in there. Among them, the labeled point, where basically we should expect to have the output as a label, and then a feature vector, right? So let's see you have your input is a bunch of columns in there that you want to do, create a model out of those columns. If you want to use ML, that's what you have to do is to restructure that data to look like a label followed by a vector of features. And there are things in ML that will allow you to do that. So you just pass in your columns and to these things, feature processing components, and then they will give you back a vector of those columns assembled like that. And at that point, when you have the label point, then you can call the machine learning on them, things like linear regression or logistic regression or anything else. We have also this dense vector. Let me try to run this. Yeah, as you can see here, if I call this dense vector, really I'm just calling for the vector to be as it is. Like 1, 2, 3 in dense format will consume all the memory as 1, 2, 3. There are cases when you have vectors that have a lot of zeros in there. So it will be a waste of memory to just store them like as dense. In that case, then we use sparse representation. And in sparse representation, this is how it looks like. Basically, the sparse representation will be the length of the vector, followed by a list of where all the indices that are non-zero, the indices of those non-zero values, followed by a list of the non-zero values themselves. So that's the sparse representation. So basically, if you have 1, 2, 3, as dense, it will be stored as 1, 2, 3. Let's say you have another vector which is 0, 2, 0. Then it will be a waste of memory to store it as dense, basically 0, 2, 0. So what do? You put it into a sparse representation. In this case, it will be 3, meaning like 3 elements, and followed by a list of non-zero indices. In this case, it will be 1 for the 2 value, followed by 2 itself. Now, if you have like huge vectors or matrices that are sparse, that really comes in handy, this sparse representation. So those are what this notebook is about. You're more than welcome to run it later on your own. It has this rating as well that you can do, but I'm not going to run it here. So let's move to the first notebook, which is 31D. And then you can follow along and run this on your own as well. I mean, you can pick Python or even Scala. So what are we trying to do in this application? It's a power plant pipeline application. And it's really about peaker or peaking power. Those are power plants that are basically there just in case something bad happened. So you have a power plant, and then you have high demand for power. What do they do? They launch these power plant peakers, just to basically cover the extra load, basically, that you have during that short period of time, and then you tear it down, basically. In this case, we have 4 columns that define this power plant, and here they are. We have AT, which is the atmospheric temperature. We have V, the exhaust vacuum speed. We have AP, the pressure. We have RH, the humidity. And then we have PE, the power output. So we're trying to predict, using Spark, how can we use Spark ML now? Because now we're trying to stay away from MLlib, because as I told you, MLlib uses RDDs, and try to stay away from RDDs as much as you can. Which means in today's session, we will be talking about Spark ML. We are trying to predict PE given the other 4 columns. That's the idea here. So let's see how we can do it. But in this notebook 30, we will skip the 3 columns. We'll just keep the temperature. We want to see if just the temperature what would give us in terms of prediction when it comes to PE. Okay, so first thing I need to do is as you can see with Spark 2, sorry, I apologize. I'm having some problems moving my mouse here. I can't see it on the screen for some reason.
Can you just check if everyone's connected? Any connection problems, issues? Anyone?
Yeah, are you all connected? Do you have all the clusters up and running? So, first of all, in order to run this, for those who are not familiar with the Databricks environment, in order to run a cell, you can either do Control Enter if you want to run the cell and stay there, or Shift Enter to run it and then move to the next one, basically, right? So when I run this one here, you can see that it just displays like text data, basically. The first line is header line, and then we have a bunch of values in there. This is how we would read the file. So let me talk about that a little bit here. In green, or the commented area, is how we used to do it before too. And the top one is how we do it now. So as you can see, in before, we were using the SQL context. But now we're using Spark. And I talked about that, right? So now SQL context is really embedded within Spark. Before, we needed to give format and then give com.databricks.spark.csv. That was a so successful package when it was released that now it is by default supported in Spark. So you don't even have to do that now. But before, if let's say you were not in a Databricks environment, let's say you had Spark running on-prem, then you needed to get that component and then change the configuration file in your Spark environment to point to it, to use it. You don't have to do that anymore now with Spark 2 because it comes bundled with Spark. You still have the option to tell it whether it has a header or not. In this case, it does. And then we can still tell it whether we want to infer the schema or not. This is something that we wouldn't do if we were talking to Parquet. But because this is CSV, then we have to do it. Unless we know the schema, then we can pass the schema in here as well. We can tell it, no, we don't want you to infer the schema. We will provide you the schema because we want to save that one pass, right? So in this case, we say, okay, well, that's okay. Just go ahead and infer the schema for us. And then we give the path of where the data brick, where the file is. So why don't you run it and see if you can do that? Or do you get an error? Does it run for you? Yes. It works? Okay. The reason I asked is, and probably your accounts have been set up already because it could have not worked, and this is why. If you look at the path in there, you see DBFS, right? DBFS stands for Databricks File System. So this is something that's done a lot by companies out there. I mean, what Databricks did is creating this layer, which is really a file system, that sits on top of S3, right? So when you have your files in S3 buckets, instead of keep referring to them like S3 column / and you give the path, it's kind of like painful, you just mount those points or those buckets into mount points, which is really a Linux thing, right? And then after that, you just refer to them as we do here, which is /Databricks-datasets, basically. So let's say in the future you are on your own, you have files on S3, then you can just mount those buckets using the BFS. So that's what the BFS does. But it sits on S3, which tries to mimic what HDFS does. You know, I mean, HDFS is very reliable. By default, it replicates 3 times. S3, it's highly reliable because it's in 11 lines. You know, it's really rare to lose something on S3 as well. And so it has those features, you know. HDFS uses co-locality, you know. When HDFS knows that this data needs to be close to this data, it tries to put it in the same machine. If it can't, it put it in the same rack. And if it can't, it put it in different nodes. But at least it tries to put it next to each other because you are in big data. Network is very expensive, right? So things like that. Amazon, for instance, has EMRFS. If you're using S3 through EMR, then you can use EMRFS as well. So this is similar to EMRFS type of thing, right? So in here, What changed from before? We did load, now we call it CSV. So I just loaded the file, and this is how it looks like, right? A bunch of columns in there, and then the output column as well that we're trying to predict. Now, let's see apologize, it's really hard for me to look at my mouse here. I don't know what's going on. Let me just do this quickly. When I unplug it, I can see the mouse. When I plug it back in there, I can't. Okay. All right, let me do this shift. Okay, so I'm going to use shift because I can't see the mouse, so I have to use shift to move to the next one. What I just did here is basically, again, we're just keeping the temperature. We're throwing away all the other 3 columns, right? So we want to keep the temperature and the output, and look at what we can have. I can do display. So here I'm using 2 things. I'm using describe, and I'm using display. So what is display? Display is a Databricks function. It's not Spark, it's Databricks, but it's a very important one. Why? Because it gives you a lot of visualization for free, as you can see here. This arrow. If I click here, if you use display, then you will have this, all the visualizations in there. You can have a bar, you can have scatter, that's the one we're going to be using next. You can have a map, even a map. Let's say you use some data, and that data is geolocated, location data, has longitude, latitude. You can just pass it to display, and then it will display it on a map for you. So you get that for free. So this is an important, and also it's based out of HTML. So the formatting is better as well, and as you can see. So we can, and then we're using describe. Describe is to get some statistical information from the data. So describe will tell us the count, the mean, the standard deviation, the minimum, the maximum. You get all that through describe, basically. Okay, so what I'm going to be doing here is something that's basically useless. But I'm showing it to you here so that you can appreciate later what we do. So if you remember, I said we need to have the data as label point and a feature vector, because that's how the code expects to see things, the data, right? In here, we have the temperature, which is just a double value, but we still have to put it in a vector feature. This is a UDF, a user-defined function, that will allow you to do that. So, and basically what it's doing here, it's registering. As you can see, I have spark.udf.register. What does that mean? First of all, I'm using Spark, which is the entry point, right? Then I'm telling it I want to use the UDF section of that entry point. Then I'm telling it I want you to register my function called oneElementVec. Why? Because I want to refer to that function from within SQL later. So if you want to call this function from within SQL, you will have to register it first. And that's what I just did here. And all my function, all it does, it takes an input, which is in this case D as a double, and then gives you back an array, a dense array. So it just puts it inside an array, basically. So this is the output now. So I just formatted my data to be like a label point. It has the output on the column, and then it has a feature vector. In this case, it's just one element vector, right? Next, I need to split the data. Now I'm making the model now, right? So I have the data, I have to split it into two things in here, which is 80% for training and 20% for testing. Usually what you do, you can also do it like 80% for training, 10% for testing, and 10% for cross-validation, because I need to tune my model later too. Because if you're not careful here, and then you just let your data to be reused all the time while you're creating the model, you can be victim of data snooping, which is a disaster in machine learning, right? Because you will be biased towards your model creation process. So in here, at this stage, we don't care about that. We have training data, and then we have 20% for testing data that we will use later. And as you can see, I am randomly splitting the data. And I'm using the seed at the end there. And the reason for that is just because even though it is random, if we keep the same seed, we can always recreate the tests, right? And then I cache here. Why do we need to cache? Very important. So let's say you are not caching. Let's say I'm doing this. I am reading from S3. I'm reading a file. And then that will create a data frame for me. And let's say after that, I do something. I do a filtering operation, right? I want to keep the odd number and throw away the even numbers. And then let's say after that, I issue an action. I do a count. I want to count how many of those even numbers I have. So I do count. What happened? Count is an action. It gets executed right away. But the filter operation does not. All it did was it got logged into that DAG, which is the directed acyclic graph, right? Which is basically just a log. So why? Because if something bad happened, then Spark can still go back to that and say, okay, I lost this partition from this node. How can I get it back? And then the DAG will say, okay, well, you have to go to S3 and get the file again and recreate it, right? So let's say nothing bad happens. Read the file, filter it, do an account on it, and I'm happy. Comes back with a value. You have 10,000 values in there. Let's say I do a count again. What happened? Spark will have to do exactly the same thing again. A lot of people, they get confused because they come from a one CPU world where they think like things are still around in memory. You are in a distributed environment. Nothing gets kept, right? So if you do count again, Spark will again go back to S3, read the data in, and then do the filter operation, and then give you the count again. If you don't want that to happen, you have to cache. You have to issue a cache somewhere. Now, that's a different problem. Where should I cache in the DAG? Should I cache at the top, or should I cache at the bottom of the DAG? That really is related to the problem you're working on. Now, if you are really computing very expensive data, right? If your expensive data happens to be in the middle, then cache it there. If it happens to be at the bottom, cache it there. If nothing expensive, then probably you cache at the base, and you'll be fine. So really, this is depending on what you're doing. But caching is your friend there. But you have to keep in mind that caching is not cheap, right? Because you are limited in resources as well. So that's why you need to know what to cache. In machine learning, usually you have to cache. Like in this case here, we're just caching those two because we can always refer to them back and forth, right? So this is what caching comes in. Then what do? We cache the data. We create a linear regression. And I'm going to go a little bit into detail of how this is done under the hood when we do the second notebook, right? But here, I want to do a linear regression. I have my data, and I'm trying to make a line go through it the easiest way in machine learning, right? And so I create the linear regression. It comes back with an LR, which is a model in this case. And then I call a fit on it. You may ask, what is the fit? But I'm not going to talk about it now. I'm going to talk about it in the second notebook, when we go into what an estimator is and what transformer is. And those are really are the cornerstones of Spark ML. So in Spark Core, we have transformation and action. Action executes right away, transformation only gets logged. In Spark ML, we also have something similar. We have transformers and we have estimators. So when you're designing a machine learning, it has to be either one of these two, either a transformer or an estimator. And then we'll talk about what those are. But the estimator has the fit function API. And that's the one we're using here because the linear regression is an estimator. So I just created the model. And then I can just pass the test data to it. So now that I have the model, which was created through the training data, now I need to test it using the test data and see what I got, right? So I basically call the transform on it because now the model becomes a transformer. And don't worry about the transformer estimator. I'll explain what they are in a bit, right? So now that we have the model, we pass the test data to it, and then it gives us back predicted labels, and then we can look here and see what they are. Oh my God, that's definitely better. Okay, so we missed. Okay, so if you remember, let me go back to here. Remember, we selected the temperature and the output. The temperature being the input column, and then the output, that's the one we're trying to predict, right? And I also use this create or replace temp view. And what that does is creates a virtual view on the data so that we can look at the data using SQL, right, later. This API call in Spark 2 used to be called register temp table, for those who are familiar with Spark. So once you load the data through data frame and you have your data everywhere on the nodes, then you can create this virtual view, which is register temp table, or after in Spark 2, it's called create or replace temp view, and you give it a name. And then once you do that, you can just refer to that as a table in plain vanilla SQL later. And that's what we just do here. So I do SQL because now, if we are in a Scala environment, that doesn't prevent us from using SQL or Python or even file system. So if you want to use Python and you are in a Scala environment, all you have to do is %Python. And then you can just push the code in there, and then it will get executed from within the same notebook. So you don't have to create a new notebook for that. In this case, we're using SQL. And then we're doing select star from the power table that we just registered as a temp table. And again, this is how you can look at it using the scatter plot. If you just select this one here, right, and then it shows you temp versus output. You can go in here and then change the settings. You know, you can move things around. We'll see that later. But for here, we're just trying to look at the correlation between the output and the input. And as you can see, this is temperature is highly correlated, linearly highly correlated to the output. Right? So we should expect, if we make a line go through this, we should expect to capture most of the information in the data. Right? So how can we do that? We've seen this UDF, so I'm just going to go through this. We split the data into 80%, 20%. We cached the data frames because we want to go back to those and we want that to be fast. And then we created the linear regression model, as you saw before. And then I called the fit function on it. And don't worry about the fit, I will explain it later. But basically, I'm just passing the training data to this newly created linear regression, and I'm asking it to give me back the model. And then once I have the model, then I pass my test data to it. And I expect to see predicted data back. And this is how it looks like. Features are represented as sparse. That's why you see that weird looking 1-1 things like that. You know, these are a sparse representation of the feature vectors. But then what do we have? We have the label, and then we have the prediction, right? So what we can do things like this. We can display this. As a histogram, right? So this is prediction minus label. So even though we are just using one column, you can already see that this like Gaussian curve thing, it shows you that just the temperature captures most of the information in the signal already, right? So you can do things like that by plotting the histogram of the difference between what you have predicted and the true labels in there. And then we need to evaluate as well. So how did we do? A way of how to evaluate on Spark ML is to create those regression evaluators. In this case, it's a regression evaluator. So when we do logistic regression, it's going to be a binary classification evaluator, right? Which will evaluate the ROC curve. In this case, what we're trying to evaluate things are like MSE, mean square error, root mean square error, which is the default one, or even R squared, or MEE, right? Mean absolute error. So because this evaluator is set by default to RMSE, we want to see how R squared did. And this is how you would set the matrix for R squared. And then you can pass the predicted values to it, and then it gives you back the value for R squared, which is, in this case, 0.89, which is not bad, right? Because R squared close to 1 is better, right? So this is the first exposure of how to use Spark ML to do machine learning, even though we haven't talked about pipelines and the fit and the transformer and the estimators, which we will do next. Any questions so far? Okay. So let's move to the next one. So in 40, which is called the Revenge of Power Plant, basically we're trying to include what we excluded from before, those three columns, and see if that will have an impact on the results, right? So again, we read the file again using the Spark read with the different options that we used before. And we can display the data, and the display functions takes care of showing you all the correlations between the columns, and as you can see. So if I make this larger, you can see that this is basically the correlation between all the columns. You can see that PE is highly linearly correlated to AT, and then we saw that through R squared. But you can also see the relationship of PE versus V, which is still a lot of, highly correlated there too. I don't know if maybe I should use a line or maybe a spline there. It depends on the complexity. If a line will gain me a lot, why would I complicate things? I can see the relationship of PE versus AP, which shows that there is still some information that can still be captured through that column. Probably RH versus PE is almost like random in there, right? Unfortunately, this display, you can only enjoy it when you have low dimensions, basically, right? If you have thousands of columns, obviously you can't do that, in which case then you'll have to go a completely separate route. Things like PCA, for instance, to reduce the number of columns to process in there. So here, if you remember, I showed you how to assemble those columns into feature vectors. And then we created our own UDF, and we had to register it with Spark because we needed to refer to that table, to that UDF from SQL. There is no need to do that. There are things, components in Spark, among them this vector assembler, which is itself a transformer, where you can just pass your input columns, and then it gives you back an output column, which is bundled as a feature vector. And this is what we use here. So basically, it takes ATVAPRH, and then gives you back a feature vector as an output. But then we'll have to call this transform API on it. And as I said, the estimators, they have a fit API. The transformers, they have a transform API. And then I'll talk more about what they do in this notebook later. But we have to call that transform API and then pass the data to it, which are those 4 columns. And then what it gives us back, it gives us back a sparse vector representation of features. Basically, we are putting ATVAPRH into a 1 vector feature in there. Again, we split the data. We call linear regression on it. And then we explain the model. So now once we created the model, I'm going to stop right here for a break, and then we will resume after break. Once we create the model, we can call this explain params, which will tell us what tuning we can do to that model. And then I'll go into a little bit talking about elastic net param and what it is, how we can use it, how we can tune it, things like that after the break. So let's stop here for a half-hour break, and then we'll resume after that. Okay, so let's resume here. What I would like to show you here quickly, just doodle some of the information. When you do a model that explain, basically, because now that we created the model has parameters that we can set. One of them is elastic net, basically, that you can also set there when we did linear regression. And so what I mean by elastic net is when you have in a situation like this, where basically you have like your y, let's say equal beta 0, x plus beta 1, where you are trying to basically make a line go through your data. Kind of like capture all the information in the data through a line. And basically, when we do a linear regression, we're looking to minimize something like this, y minus beta 0, x minus beta 1 squared. So we are minimizing the distance squared, right? And the best line that gives us the minimum there will be the best line to pick for our solution. But if we are not careful, and then we don't put any constraint as a regularization on that, then we may very easily overfit, basically where you end up with a model that we call high variance. So low variance, low bias, high variance, meaning like you are reaching all those points. So if your data is like this, you may end up with something that you're trying to follow your points in the data, right? So if you're not careful, you are reducing the bias, but your model is becoming very high variance, which is a danger. Why? Because if you throw away all the data and then you bring a new test data, your model will fail completely, right? So what do we do to reduce that overfitting concern is to add some regularization parameters here, right? So we can add lambda. We can add a regularization around beta 0, beta 1, governed by the lambda coefficient in there, right? And given that the sum of these two is less than a certain cost, let's call it S in this case. So what are we doing graphically? That's why I picked just beta 0, beta 1, just keep it simple. What we're doing basically is something like this. So we have basically, we are bound by the circle given by beta 0, beta 1, right? That's the constraint that we put, the regularization to constrain the overfitting. And let's say our curve, the minimum that we're computing, which is the curve, the contour of the cost function, is something like this. then we are looking for these points here. Right? Those are the best points where basically, and in plain English, what we're doing is if we have like many features in there, we're pulling those features down towards that circle. Right? So we are really putting some constraint there. And as you can see, given this graph here, is that those points, they can be on axis, but usually they are not. So what do? We set a threshold. And then we say, if it's less than this threshold, just knock them off, right? So this is ridge. This is basically a ridge constraint, right? What if we don't use lambda beta 0 square plus beta 1 square, and instead we use lambda absolute value of beta 0 plus absolute value of beta 1 as a constraint? So this is harder mathematically because it's not the square, it's not there anymore, right? It's not derivative as the absolute value, but graphically is interesting because graphically what we get a diamond now instead of the circle. And then the cost function needs to meet the diamond only on the axis. And this is the interesting part here. So the join now of the cost function would be something like here, or here, or here, right? And each time it meets the diamond on the axis, which means you are knocking off features in there automatically, right? And this is lasso, right? So this is lasso. So lasso is great when you want to do some kind of like feature selection automatically. Sometimes, you know, I mean, if you are in a very high dimensional space, it's good because you may end up with a sparse matrix. But sometimes you don't want that. You don't want to knock off all the features in there. You want to knock off some, and you want to keep others. So what do? We then create this notion of elastic net, where basically we say we will define our elastic net as 1 minus alpha times ridge, which is L2, plus alpha times L1. So we create this kind of like, combine the two together. When we don't want to knock off everything that lasso kills, we want to keep some of it through ridge. And then we create this. Now we are in control of alpha. If alpha is set to 1, in this case we keep only lasso. If alpha is set to 0, we only keep ridge. But then we want to be able to be in between the two extremes there. And then we can play with alpha being between 0 and 1. And that's elastic net, and that's how it's implemented on Spark as well. So you are given control of alpha on Spark, and you can tune that along with lambda as well, right? The regularization parameter in there. So you can tune lambda, you can tune alpha, and then that's what you get through that explain param call. By default, alpha is equal to 0. So by default, Spark uses ridge, which is not surprising because if you look at all what's offered out there, even Amazon Machine Learning, they use ridge by default because it's just easy to work with. So instead of just knocking off the feature, you just set a threshold and you just use ridge instead. Another thing that I wanted to point here is because we're doing, I go back to that y equal beta 0, or in this case beta x, if we're using a matrix representation, I have a bunch of them. In this case, I can resolve this, right, through a closed form solution, in which case I'm looking for betas, and I will have to find this, x transpose x minus 1 x transpose y as a solution. So this will be my solution as a closed form solution, which is great. What if I can do it in case where I cannot invert, because it's just a huge matrix? So what do? With Spark, if you have up to 4,096 columns, it uses the closed form. Beyond 4,096, it uses gradient descent, stochastic gradient descent to find the solution for you. So that's why if you look at the code, you may get like confused what's doing there. But basically that's in a nutshell what it's doing. You know, it's trying to find the closed form solution if you have less than 4,096 columns. Otherwise, it uses stochastic gradient descent, where basically, because this is a convex case, linear regression, you are looking for this minimum by starting somewhere, and then you keep descending over that minimum somehow, right? So this is how it's implemented on Spark, this linear regression, yes? I think just because of, some benchmarking was done and limitation on the compute probably. Yeah, just a number that's out there. Maybe it'll change in the future, but so far that's what it is. Yeah. Okay, so let's go back to there's no specific reason. He's asking almost the same question as my friend there. There's no reason behind it. It just happens to be that number. I wouldn't be surprised if it changes in the future. But that's what it is set to at this time.
Yeah, because the common technique is for large matrices, you make 4 quadrants and you recursively invert every quadrant.
Yeah.
And keep doing that.
Yeah. Well, when you are probably in a distributed environment, just very costly when you start moving data on the wire. That's probably what the biggest constraint that you have. When you are creating code for something like Spark, for instance, or as a matter of fact, Hadoop, your biggest problem is really shuffling the data around, right? So as soon as you start shuffling the data, it becomes very costly right away. And for instance, I can give you an example, like when you use like reduce by key versus group by key. Both of them, they can do the same thing, but the difference is that when you do reduce by key on Spark, it is doing a mini combiner, is exactly like Hadoop. At each node, it's trying to do the combiner, the reduce first, and then shuffle the remaining data around, instead of group by key, where it shuffles all the data around, which is a very expensive operation. So when you're creating code on Spark, this is the first thing that you need to look at, those shuffling data around. So if I go back here, so and then you do explain param, this is what it gives you back, like elastic net param. In this case, it's in the range of 0, 1. Alpha is 0 is penalty L2. Alpha 1 is L1 lasso. And then you can control it between 0 and 1. It also tells you other stuff like features, the name of the features column. By default, Spark is looking at features as a name, unless you change that, and you can do that as well. So those are the things that you can control through this parameter here. Like in here, we're setting it to BPE. Now, look at this. If I run this, I have the training data, and then when I run it, it fails with an exception. And the reason is because Spark, machine learning, or ML, was expecting a label and a feature vector. And that's not the case here. So what we need to do is really to assemble the feature vector first, and then call it later. And that's what we do here through this. Okay. So as you can see here, I'm calling vect assembler. I'm calling the transform API on vec assembler, and I'm passing the training set to it, and it's giving me back that data structure, the label point and the feature vector, which I then call the fit function on the LR. So let me talk about what those are. So as I said before, in Spark we have actions and transformations, right? Actions, they execute right away. Transformation, they only get logged. In Spark ML, now because we have the schema, we have two components in there. We have estimators, and we have transformers. What's an estimator? An estimator is a complex component that really implements the logic behind machine learning or the algorithm that you're trying to implement. So let's say you are trying to implement linear regression. So the API provides you with a way on how you add the logic of the linear regression, and then you will have to advertise the fit function as an API call. It's really a black box. Let's say you have your own secret sauce machine learning that you want to do, then you can look at the code of how linear regression is implemented as an estimator, and then you will have to add your code in there, but you will have to provide the fit API, so that if you give me that, I don't care about how it's done inside. All I care about is you give me the fit API, I pass my training data to it, and I expect to see back a model. So an estimator takes a data input, in this case training data, and gives you back a transformer, which is in this case a model, right? That's what we're looking for. So through a linear regression estimator, we pass in training data, we get back a linear regression model. We do the same thing for logistic regression, for decision trees, and for all of the other stuff. So the output from the estimator, which is a transformer, what it is, a transformer is really a component that takes data in and then transforms it and gives you back a data out. So it takes a data frame input and gives you a data frame output. If it's a machine learning transformer, in this case, it would be like the LR for linear regression, it will take test data in, and it will give you predicted data out. If it wasn't a machine learning transformer, and we have a lot of them there, many of them there, things like the VEC assembler, transformers that are just transforming the data to do something. In the VEC assembler case, we are taking data as columns, and then it's giving us back a vector of those columns assembled. There is another VEC assembler, there is another transformer called tokenizer. You're doing some NLP, natural language processing. The data is a document. You make it go through the tokenizer, reg tokenizer, and then it gives you back a data frame of just those tokens output. Yes? No, the schema is, the question was, do you provide the schema to the estimator, right? No, you don't do that, because you are already working with data frames, but the estimator is doing some schema validation inside as well. Yeah. So now you have the estimator, and then you have the transformer. You can go and look at how the code is implemented, and then walk you through the source tree later, show you where the Spark code is, and the estimator code is, and the transformer code is. If you go to look at the linear regression estimator and try to understand so that you modify it to add your own code, it's probably going to be tough, just because of those cases, like closed form solution versus SGD versus things like that, right? A better estimator to look at, which gives you more, which is easier to understand, would be the string indexer. And in the string indexer, basically, what you're doing is you have a list of elements, like let's say A, B, and then what the string indexer will do, it will assign an index to the most frequent one. So in this case, it will assign 0 to A because it happens 3 times, and then it assigns 1 to B because it happens only 1. So if you look at the string indexer and how it is implemented, then it will probably be easier to understand how you can modify that code. So again, in Spark ML, you have only 2 components, estimators and transformers. You use an estimator to create the machine learning model. Right? Then you use the transformer to modify, using that model, modify your data. The estimators, they are not just to create the models. You use them also to do cross-validation when we do the pipelines later. right? Because even those, they have a fit function. So anything that has fit is an estimator. Anything that has dot transform is a transformer. And that's what I'm going to see next. So in this case, LR has a fit. So it's an estimator, right? Now, if you look here, you will see that this is the first time we're looking at the pipeline. This idea of using the pipeline is really was kind of like borrowed by scikit-learn, from scikit-learn, right? So instead of creating your own code to do the linear regression or all those pre-processing steps, like let's say you are doing NLP, you have to do tokenizer, you have to do stop remover, you have to do normalizer, you have to do all that stuff until the very end when you hit the machine learning model. Let's say you're doing k-means, then you'll have to take care of all connecting the dots yourself. If you do it through the pipeline, what you do, you create the pipeline as an estimator, and the pipeline has one extra API that it provides, which is the set stages. So basically, you just call set stages on the pipeline, and then you tell it, okay, I'm going to give you component 1, component 2, and then component 3, component 4, and then at the end, you call the fit function on it. And magically, it will call those components for you, and then it will, at the end, call the fit function and give you back the model to use. If you're using a cross-validation pipeline, let's say you created your own model, now you're happy with the betas, but you still have to tune them through a cross-validation, then what you do, you create a pipeline for cross-validation, you stick through set stages the model pipeline in there, you stick another component which is for the grid, for the parameters that you want to use, and then you call the fit function on the whole thing. And basically what it does, it will execute the inner pipeline to create the model through those components, and then it will call the fit function to test the grid now using cross-validation, and then at the end, it will give you the best model to use. In which case, you can just grab that model, and then if you're doing like creating a dashboard, for instance, you create a Spark streaming application, and then each time you receive data, you can just apply the model to it, and then update in real time your dashboard. You can do things like that. So in here, we're creating this linear regression pipeline. We are setting the stages just for the VEC assembler and LR. So we have already created the model, right, for LR. We needed VEC assembler because we want to assemble those columns into vector features. And then we call the fit function on it, on the training set. This is if we want to look at the intercept of what we did from our model, right? So you can call LR model, which we just created, dot stages 1, because if you remember now we have two components inside the stage. We have VEC assembler at index 0, and then we have LR at index 1. So we are basically looking at index 1. And then as instance of, we are casting here that model to be a linear regression model. This is more like a Scala thing here, where basically we cast the model to make sure it is what it is. And then we call intercept on it, and that's the result it came back with, 455.145. We can do the same thing to get the coefficients, right? So if we get the coefficients here, we can see that we have the temperature, which we saw was highly linearly correlated to the data, came back with 1.97, right? And the other ones, the remaining three columns, they were 0.23, 0.06, and 0.15, when we see that 0.06 was almost no influence or no impact on the output, on the power output. And then you can also call this VEC assembler get input columns, kind of like to help you match which one is which. In this case, we can see that AT is the first one and RH is the last one. Okay, any questions so far? Okay. Again, we saw this described from the previous notebook, where you can find the mean, the standard deviation, and all that information. And now we are ready to apply the test data to the newly created LR model, right? And this is what we get back. Now, this is, we saw earlier in Notebook 1 how to create an evaluator, because now Spark allows us to create those evaluators, right? To get the RMSE or the R-square, all that stuff. In this code here, it's just showing you how you can also do it the old way, using the RDD. And then we created this print stat function, where in which case it's really dropping down to the RDD and then doing the map and calling that regression matrix, and then finally returning RMSE, explained variance and R-squared. And then we can print the stats here, and then we can see that our R-squared went up from 0.89 to 0.92, which wasn't like a big deal adding the 3 columns in there, but that's how you would do it, basically. So for this last part, I will give you a few minutes to try it on your own and have a feel of how it works. And basically, this will allow you to change lambda. You can set it to 0.02, and then look at the output and see if that had any impact. It will also allow you to change the elastic net param to 0.1. Basically, instead of just using ridge, we're using ridge and lasso together, and see if that has an impact. So I'll just give you a couple minutes to try it, and then we'll go from there. Yes?
What's a typical value range for lambda? So we
Depends on the data and the case that you. Yeah, what's the typical value for lambda when you're tuning? When you are in a supervised word, the only best tool that gives you that answer will be cross-validation. So basically, you'll have to go through cross-validation and find that answer, those values. Okay, so I did run those 2 cells, and it came back with an R-squared of 0.92, which didn't change much for me, but the idea here is really to tell you how you can play with those parameters and change them and see the results. Even though this is not the right way of how you would do things, right? Because we're hoping that cross-validation will do that for us. I'm just showing you that you can still do that. Even manually, you can still do that. All right, so yeah, okay, so this concludes the notebook number 40. Any questions so far?
How about the aggregation types?
Like what kind of aggregations? Is that the question?
There is a parameter, when you explain the parameter, the first parameter is aggregation depth for the linear regression.
Oh, let me go back there.
Could you repeat that, please?
Yeah, how about the aggregation type? I'm just still going there. Is it the bottom?
Up, there is a explain parameter of.
You mean here?
The place you stopped before this section.
Keep scrolling up. Where is it? This last one?
The first line,
Oh,
aggregation depth.
oh, this is aggregation depth, suggested depth for a tree aggregate. I don't know. I mean, maybe this has something to do with the tree itself. I don't know. I mean, we're using linear regression here, but this would make sense to me if we're using the tree, because if you're using the tree, we'll see that later in the afternoon. Really, that's the only parameter that you can tune to avoid overfitting. Because if you're not careful and they'll just keep growing a tree, and you're not careful about how many levels, then you can easily overfit. Right? So that probably will be set in that case. So let's go to the next one, which is logistic regression. Yes?
Just remind students that there is a Q&A.
Yes, yes, thank you. So if I go back to your students file, and at the very bottom there is this question and answer document, and there is a link to it. If you click on it, it will take you to this document, which is Q&A parking lot file, where basically you can add, and I see already a few questions that have been added in there. You can add any questions that you have that we cannot answer today. You can add it there, and then we'll make sure to follow up on it. Okay, so in this notebook, we're going to be looking at logistic regression. So basically, if you have data that we cannot model through a line, right? We can have cases like you have data that looks like a lot here and a lot here and nothing in between. So modeling that through a line, it just doesn't make sense, right? Because you may reduce some of the errors at the extremities, but then errors in the center will be huge. So what do we do in this case then? Instead of looking at linearly or through a regression, use a line, then we look at the data as if we use a probability. In this case, will makes more sense, where basically we are saying like if the data, what's the probability of the data, what's the probability of the data happening here, or what's the probability of the data happening here, the one that I'm trying to predict. And in which case then logistic regression makes more sense, because now you are not relating y through beta 0 x beta 1, but you are relating y to x through a probability, basically, right? And then we can use a sigmoid. That's what logistic regression is defined under. Basically, it's a sigmoid, which is the inverse of the logit function. And then instead of using least square errors to measure how good we are doing, then we use a vote, maximum likelihood in this case, kind of like to decide whether we did good or bad. And that's basically what logistic regression is in a nutshell. So in this notebook, we will be using text, right? And we have like 20,000 Amazon reviews. And we're trying to measure sentiment through those reviews. So let's first read the data, take a look at how it looks like. And this is how it looks like. So it has a rating column, right, from 1 to 4, or actually to 5. And then a comment which is in text to tell you whether the client was happy or angry about that product, basically. We're not trying to, yes?
Question. In this example, you're not using the database FS part in the path. So does that not necessarily...
I'm sorry, I can't hear you. I'm sorry. Sorry. Yeah, sorry.
So in this example, you're not using the Databricks FS part in the path. Does that not necessarily matter once it's mounted, once the
Yes, when it's, yeah. The question was, because we saw that earlier in the first notebook, I think, where we did the BFS It was a call to using DBFS. So his question is like, now we're not calling that. Does that mean that we don't need to do it when this is mounted? And the answer is yes. So once you mount those S3 buckets through DBFS, you can just refer to them in paths like /databricks dash datasets, which is already mounted here. Was that the question? Yes, thank you. Sorry about the noise too. I mean, no control over that. So now we have this data set, which has a column of ratings and then a bunch of text in there, or reviews. We're not predicting the rating in this case, because to do that, you need a really large data set. But what we're trying to do here is a different set of problems. We're trying to use binary classification, meaning like we want to know whether we have a negative sentiment or a positive sentiment. And how do we do that? We look at the ratings, which are 1, 2, 3, 4, 5, and then we'll just bucketize the ratings into two classes. So anything less than 3.5, in this case it will be 1, 2, 3, will be considered negative. And anything above 3.5 will be considered positive. Will be like 4 and 5, we will say this is a positive sentiment here. So we turned our problem from NLP or rating prediction into a classification problem using logistic regression in this case. And so we'll see how to do that. Now, what's interesting about this notebook is that in order to apply logistic regression, we'll have to do some pre-processing to the data, right? So we'll have to tokenize the data because this is text. We will have to remove the stop words. We will have to count vectorize, keep just the most important ones of those words. But basically what we're trying to do is try to see if we can have the words themselves impact the decision on the class selection, whether it's negative or positive. So that's the whole idea here. So we will be exposed to how to use NLP on Spark, as well as to how to do logistic regression. So let's start with this. By the way, this is missing, was accidentally missing from your notebook. So if you want just to copy this, you can just create a new cell, and this is how you would do it. You just hover here, and then you'll see a plus sign. You just click on it, and then you'll have a new cell in here. And I want you to basically add this. So we are using SQL. Is it clear at the back there, or should I make it bigger? Okay. How about this? Okay. So here we are using plain vanilla SQL to select count rating from this table reviews, which we created. This is a temp table. And then we are grouping by and ordering by rating. So this is how it looks like. Yes? Have a question? Okay. So before I talk about the results, and you can look at the results here, I don't know, are you done copying this line? Okay, sorry. Before we talk about the results and how they look like, I would like to point out something here, which is not related to machine learning, but it's really part of Spark. If you expand the job 316 in my case, you see the word job in there. Now, job means action, right? So if you open the UI, right? If you open the UI through here, which is very easy to do on Databricks, you can just open the UI here. You will see tabs in here, right? So you'll see one for jobs, one for stages, one for storage. If I click on it, I have some stuff that's already cached in there. And then you have a tab for environment, which is usually not important unless you want to see how your environment settings are. And executors, in this case, we have only one, which is the driver and the executor, both the same thing, running together, right? As it shows here. The driver is itself the executor in this environment. And then you have this tab here called SQL, where basically you can click on it and then look at the details of what the catalyst created for you. If you remember that blue graphics in there, logical plans, physical plans, you can look here and really look at what was the logical plan and what was the physical plan and all that. And then there's this JDBC ODBC tab where it shows you all your connections to the databases. And when it's missing there, which is for streaming, it only shows up when you are really doing streaming, right? So if you do something that has to do with streaming, then a new tab will show up there. Why I showed you that is because if you look under jobs, it will give you a list of all the stages that happened. So a job is the action. So if you have something like reading from S3, and then you create a data frame, and then you do a transformation to that data frame to create another data frame, and then you do count at the very end, count is the job. So job and count are synonymous here, right? And stages is really where Spark does something through an action. If that thing is narrow transformation, meaning like it only needed one parent to get the data from to do that transformation, in that case, it doesn't need to create a new stage because it doesn't need to shuffle the data, right? So let's say you are doing filtering. Let's say you read something from S3, and that thing is 1, 2, 3, 4, 5, 6. And then you do something like, okay, I want to keep just the even numbers. I want to throw away all the odd numbers. In that case, Spark knows that all it needs is just that data. It doesn't need any other data from any other parents. In that case, it doesn't need to create a new stage. So it just sticks the filtering process within the same pipeline. Now, if you are in a wide transformation, things like reduce by key, where you have to move the data around over all the nodes, then in that case, you are in a wide transformation case, and Spark decides to create a new stage. So you will see, if you go back here, you will see that in here, Spark decided to create 2 stages, right? 8 out of 8 and 200 out of 200. So why do we have 8? Because when Spark reads data from the source, it tries to copy the partitioning scheme from the source. So if it's reading from HDFS, and we know that HDFS by default partitions on 128 megabytes, then it will use that number as a partitioning scheme. If it's reading from Cassandra, it will try to use that partitioning scheme. If it's reading from S3, in this case, it's like 32 megabytes, right? So you are kind of like constrained to use the partitioning coming from the source. Now, once you have the data frames, which are partitioned, and then you try to do something after that, then you have to tell it how many partitions you want to use. By default, it is 200. So that's why you see 200 in there, because that's the default value. That said, 200 is a good one if you are in a real cluster. Probably it's problematic in our environment because we are using just 8 threads. So that's not good. That said, you have the option of changing that as well. So this is a configuration value that you can set to anything you want. Right? And you can change that. So I wanted just to point out this so that you know if you expand that and you see those numbers, they make sense to you. Now, if we go back to look at the results, so what did we do here? I basically displayed, so let me rearrange things. Yeah, reading accounts, okay. So basically here, I'm just looking at the data, it looks bad, right? Because of my use case, I'm trying to split the data between negative and positive. And in this case, we can see clearly that 1, 2, 3 don't cover as much information as 4 and 5. So we have a lot of 4 and 5s versus 1, 2, 3. So this is really skewed data in here. A solution probably in real life will be stratified sampling, where basically you'll have to resample the data to balance it. We're not going to do that here. So we're going to keep trying. What if we add this one here? So you still don't have this as well in your notebooks. If you just, and I apologize for that, those were left out. We have 3 that were missing, but they are very similar. So this is exactly like the first one. Let me just copy this over up here. So now we are using like great. So in that text, those reviews, we're searching for the word great and see if that will give us a data set that we can work with, right? So here is the line. And here's how it looks like. As you can see, it's still bad, right? We still have a lot of file. Actually, that's even worse than before. So let me do this. I'm going to have to copy this. Maybe that's probably the easiest way to your file at the very bottom here. My data is different? Okay, so let's look at that. So let me copy these 3 lines so that you don't have to write them down. So I'll just paste them into your file. And we have one more. Right here, okay, yes. So now I want to look at poor instead of great as before. And then if I change that from great to poor, this is how the data looks like now, which looks more balanced to me. Right? So this could be like a good starting point for us to create that logistic regression model that we're aiming for. Yes? Are you talking about this one here? Yes, you can. Yes. The reason we're doing it here is because, first of all, is we don't have time, and just to get something as quick as possible to play with. That's the idea. But yes, I agree. Yeah. And the best solution here will be stratified sampling, right? Because that will be the true thing, right? But we don't have time to do that here. So now that we have this data set that looks like this, it looks at least nicer than before. We can, in this paragraph here, we're asking ourselves, like, what should we use for this specific case? Obviously, we're using a logistic regression because that's the name of the notebook, but we are not just forced to do that. We can use, for instance, linear SVM, for instance, right? Where basically support vector machine, we're looking for those planes and those support vectors that guarantees that buffer, right? That could be an easy one, a better one, SVM, especially that SVM gives you all full control over all the kernels and that you can create. We can even use something like linear discriminant analysis, basically, where we are making the assumption here that each column is a normal or a Gaussian function, right? Except that each column will have its own mu, its own mean, but then we are making the slight assumption here that all the standard deviations are the same when we do linear discriminant analysis. So if we try, and this is kind of like not a bad assumption, because through the limit theorem, right, the central limit theorem in probability, if you make an experiment go to infinity, you probably end up with a normal-looking function there, or Gaussian-looking function. So it's not that bad as an assumption. So we can use linear discriminant analysis here. Linear discriminant. Yeah. We can use the discriminant analysis here. We can use SVM. Maybe this is a linear case. If we wanted to use nonlinear, maybe we can relax that constraint on sigma, on the standard deviation, and have each column has like a Gaussian form, which has its own mu and its own sigma, in which case it will be QDA instead of LDA. But in this case, we just picked logistic regression as an example. So how do we do that? First, we need to create those components, because now remember, we have this concept of pipeline, which has a fit function that we will call later. But then we need to create those components first. And in this case, we need to create the tokenizer. So we have text. We need to tokenize it. And this is how we do it. We set the input column to review, the output column to tokens, and then we set the pattern we wanna work on. In this case, like white, blanks, things like that, right? Then we do a stop remover. After we tokenize the text, we need to remove all those stop words. This is how you would do it. You would call stop words remover, and if you don't pass in your own list, Spark will use its own default one, and then we'll see how it looks like. But then you have also the option of passing in here your own stop words list. And at the end, we use this count vectorizer, which basically we define the input column as stop word free, and then the output column as features, and then we just keep the first 1,000 most important ones, right, through this vector count vectorizer. So we just did that. Now we can look at the list, the default list that comes bundled with Spark, stop removers, and this is it. We have I, me, myself, you know. But then it depends on your case, it depends on your industry. You can create your own list and then just add it to the stop remover at the creation time. So before we move on, and probably this will end the session before lunch, how about if it says here, scratch area to try out the feature processing steps? So let me tell you what it means. We talked about Spark ML being really two things. Estimators, really, when you are trying to create something through the fit API, or transformers, where basically you have a data frame input and a data frame output, and then you modify that somehow inside that transformer. In these three, tokenizer is a transformer, remover is a transformer, and count vectorizer is an estimator. So basically, see if you can call them, you know? Like if we do something like this. Let's just create one here. Actually, let's just go back here. And I do transform, and then I pass in data, right? I can see that what Spark did, it took the existing columns, right, and it added a new one for me. That's what it says, one more field. So if I do here, if I do show, this is what it did. It took the input, the data, and then it created this new column for me called tokens. And that's exactly what I expected here, right? So I took a line of words, and then it broke them down into worked, comma, as, comma, and so forth. So that's the idea here. Can you do the same thing with stop remover and count vectorizer? And see if you can add extra columns and then use the show commands in there and see if you can look at the data. And if that made sense. Like, we expect stop remover to remove things like this. In the second line, we should expect this to disappear, for instance, right? So let's see. So if I do something like this, let's call this df1 equal that, remove the show, and then I do df2 equal, what did you call it? Remover. Remover, and then this takes df1. Then if I run this one, dot transform, sorry. Now I can see that Spark added 2 more columns to the original one, because we saw +1 field or 1 column already. Now, because of the second call, we're adding 2 more columns. Now, if I do show in here, this is what I should see, right? So tokens now, it's worked as this mouse, and then stop word free, this disappeared, is disappeared in the second line, right? So let's stop here. I want you to do the third one. The third one is an estimator. You wouldn't have to call the fit function on it. So let's do that after lunch. So we'll stop here for lunch now. Unless, do you have any questions before we break? Okay, all right. Thank you.